This is problem 10 from chapter 17. In this problem, the pendulum consists of a 4-kilogram circular plate and a 2-kilogram slender rod. We want to determine the radius of gyration of the pendulum about an axis perpendicular to the page and passing through point O. Okay, so that axis is here coming out of the page. And remember the radius of gyration, we saw that earlier in this section. We haven't used it yet, but you can find that by taking the square root of the moment of inertia over the mass. So this is going to be the square root of I over M. Now, in this problem, we're not going to be using equation 17.1 or 17.2 to find the moment of inertia. We are going to look at what they give us in the table at the back of the book. So we have two different pieces to the pendulum. We have the rod and we have the disc. So I'm going to find the moment of inertia for the rod and the moment of inertia for the disc and add those two together to get the total moment of inertia. So that was something that they told us back on page 415. So if the body consists of shapes such as simple discs, spheres, and rods, you can just find the total moment of inertia by adding all the individual moments of inertia together. And this was also where they had the equation for the radius of gyration. So now turn to the back cover of your textbook, and we have a slender rod, and it's rotating about one end, which would either be x prime or y prime, and the moment of inertia about x prime or about y prime is 1/3 times the mass times L squared, where L is the length of the rod. So this is 1/2, or sorry, this is 1/3 for rotating about the end, times the mass of the rod, which is 2 kilograms, times the length of the rod squared, and the length of the rod is 2 meters. Okay, so that's for the rod. Now we got to do the pendulum, which is a disc. I'm also going to have to use the parallel axis theorem here because they don't give me the disc rotating about a point that's at some distance away, but I can figure that out using the parallel axis theorem here. So I'm going to take the moment of inertia about the mass center and add to that md squared, where d is the distance from the mass center to the axis that I'm looking at. So here we have the mass center here, which is a distance of, the radius is 1, no, the diameter is 1, so the radius is 0.5, so my axis is 2.5 meters away, so it's the radius of the disc about the mass center plus the mass of the disc, which is 4 kilograms, plus 2.5 meters squared, and that comes from the parallel axis theorem, which is equation 17.4. Okay, so now we go to the back of the book, and for the thin disc rotating about an axis which is going through the mass center, that is 1/2 times the mass times r squared. So this is 1/2 times the mass, which is 4 kilograms, times r squared. R is 0.5 meters. Okay, so now we got to calculate the moment of inertia for the rod and for the disc and add them together. So for the rod, I get 2.666 kilograms times meters squared. For the disc, I get 25.5 kilograms times meters squared. Then for the total moment of inertia, about 0.0, I add them together and I get 2.666 plus 25.5 kilograms times meters squared gives me 28.166. Then I got to find the radius of gyration, k, by doing the total moment of inertia divided by the mass. If the disc here is 4 kilograms and the rod is 2 kilograms, the total mass is 6 kilograms, and that gives me 2.167, and the kilograms cancel out and I take the square root, which leaves me with units of meters. So there's my answer for problem number 10.